Welcome. Okay, I have your exam twos from Provo, and we'll pick up the Salt Lake Center ones today. I have not yet gone through the multiple choice to make sure that there's not a problem with the key, so the score sometimes changes. Run out. I'm not sure if I'm really terrible at entering the key or if the testing center website is like Learning Suite and just hates me and changes things after I put it in. But you should know that sometimes the scores will change. Okay. 3, how many weeks do we have? 3. Is it less material than Unit 2 or Unit 1?
So.
Not. The pace does accelerate. In part, we can do that because the concepts and the connections that you've used from Unit 2 definitely apply to Unit 3. But it's only vocabulary. Or we use different vocabulary. I've debated back and forth about different ways to approach it, and this is what I decided. We're going to throw all of the terminology at you today. So this is going to feel a little bit like Chem 105, where your job is just to figure out what the heck the professor is talking about for the whole time, right? But once you get these ideas and these fundamental things down, everything will get easier. It actually makes more sense to give it all to you in a big chunk, then work on sorting it all out. Once it's sorted out, this stuff isn't that hard. It's really just a continuation of what we did in Unit 2. The task is to take your ideas from Unit 2, vocabulary from Unit 3, and mesh them. That's what we're trying to do today. Okay. So Unit 3 is all about the thermodynamics of acid-base reactions. Those of you who took Chem 105 more than 2 years ago had a brief introduction to acid-base chemistry the week before finals. The Chem 105 professor finally recognized that there's too much material in Chem 105. That's an understatement, right? Took out that material. They also recognize that by the time students make that stage of the semester, so they weren't learning it. Okay, so some of you may have seen acid-base briefly. It's okay if you don't remember it. What's an acid-base reaction? It's simply one where a proton needing a hydrogen without its electrons gets transferred from one molecule to another. And you can always look at the reaction and just deduce that it's an acid-base reaction. So for example, we start with HCl, we react it with ammonia. If you track the products, HCl loses the H, right? Becomes chloride. Let's go back and just show you the Lewis structures and try to bring kind of to your mind things that you may not have thought about for a while. If we look at the Lewis structure, how do I know that that's the Lewis structure of hydrochloric acid? Go back to your Chem 105 knowledge, which you may or may not still possess. You can look at the periodic table and know that chlorine as an atom has how many valence electrons?
7.
7. How many does hydrogen have? 1. So when those come together, the single electron on hydrogen and the single electron on chlorine combine to form a bond, and that becomes the bond, the line, right? Okay, if HCl is becoming chloride, the chlorine is negative because it has one more electron than it had in the neutral atom, which means that it took both of the electrons from the bond. That's how HCl becomes chloride. which means that what's coming off is the proton. Here's language that we use for this. Hydrogen atom without its electrons is just a nucleus, right? Tell your neighbor how you know that.
Probably have first one.
So hydrogen, as an atom, has only a single valence electron, right? It donates to the bond. Leaving the electrons in the bond behind when it leaves, what we actually have is an H plus, which is a hydrogen nucleus, because there's no more electrons in that. Okay, so go back to ammonia too. The Lewis structure of ammonia. Nitrogen has, that's too many, 5 valence electrons. Hydrogen has 1, so we can make 3 bonds to hydrogen on nitrogen. Is it a lone pair? Now, lots of times chemists write the structure of something, and they're not really drawing the Lewis structure. They're drawing a modified formula. So they leave the lone pair out. Helpful for acid-base reactions to think about the fact that the lone pair is there. Okay, if the H plus is being given off of the HCl and attracted or bonded to the ammonia, where's that H plus going to go? To the lone pair. The H plus needs electrons, right? And the lone pair on the ammonia is where that H plus is going to go. But what happens is that the lone pair forms a bond to the H plus. Okay. Now, why does that change the formal charge on the ammonia molecule? This nitrogen doesn't have a formal charge. Do you remember how to assign formal charge? Okay, formal charge is the difference between the number of electrons that a neutral atom has and the number of electrons that that same atom has access to fully in a molecule. And this is how we assign it. So we look at an ammonia molecule and we say nitrogen owns both of those electrons in the lone pair, right? How much of the bond can we say that nitrogen owns? 1 electron, right? We can assume it's a covalent bond, so those electrons are shared. So the nitrogen owns half of each bond, or half of the electrons in the bond. So nitrogen in the ammonia molecule owns 2 electrons, 3 or 5 electrons. That's how many it started with, has a 0 formal charge. When we compare to the ammonium that we form when the proton gets transferred, how many electrons does this nitrogen really have access to? 4. It started with 5, it's short 1, so what happens to the formal charge? It comes a +1. So if we go back to the structures on the board, what that means is, I'm not caught on the chair, that helps. Okay, so an acid-base reaction is one where an H plus is transferred from one molecule to the other. When the H plus is lost, a neutral atom becomes negative. The molecule that accepts the H plus is a positive charge because it's gaining an H plus and we get ammonia. Okay. So an acid-base reaction is really just a proton transfer. That's all it is. Okay. Let's see if I can get slides to work. Now, acid-base reactions were one of the things that alchemists knew about. So back in the dark ages of chemistry, which actually wasn't that long ago, people studied acid-base reactions. And one of the people that studied acid-base reactions was our friend Arrhenius. How did we meet him before? Arrhenius equation. He studied kinetics, right? But he also studied acid-base reactions. And he generated one of the first descriptions of what might be an acid-base reaction. And this is what he said. We can categorize something as an acid or a base by saying if you take a bunch of a molecule or a substance and you dissolve it in water and it comes apart, generate protons that are free floating in solution, then that's an acid. He also said that if you take a base and mix it into water, what you get is a bunch of hydroxide ion. Now, I think H plus really is free floating in water. Why not? Why does that feel wrong to you?
Water's polar,
Water's polar, so what's water going to do to the H plus?
attracts the negative.
It's going to attract it, right? What you actually see, what Arrhenius called H plus, is actually H3O plus, or what we call hydronium ion. Tell your neighbor why H3O plus has a positive charge. Call back your 105 expert. So if we look at H3O plus, how many valence electrons does oxygen have as a neutral atom?
6.
6. How many do we have here? 3, 4, 5. It only has 5. It has a plus charge. Now, because the oxygen has a positive charge, can we say that the whole molecule has a net positive charge? Yeah. So that becomes an ion. Okay. We have a better definition that we use now. It isn't the Arrhenius definition. It applies to more than just acids and bases dissolving in water. Called the Bronsted-Lowry acid-base model. Why is it called, like, why is it named after two people? Or is it named after someone with a hyphenated name? Ladder?
Covered it at the same time.
Yeah, they both get credit for talking about it and discussing it. So we hyphenate their name when we give the model. Okay, so the Bronsted-Lowry definition says an acid is anything that can give a proton away. And a base is anything that can take or accept that H plus. Okay, so if we're tracking this reaction here, evaluate that. Tell your neighbor what's giving the proton, what's taking it, therefore what's the acid and what's the base.
Becomes the base.
If we track here, the HCl becomes chloride ion, so it's losing a proton, right? And the water becomes hydronium, so it's gaining a proton. This is what we're actually seeing happen. So if HCl is the acid because it's donating the proton, and water is the base because it's accepting the proton. Can this reaction run forwards and backwards? I mean, any reaction can, right? If we're running the reaction backwards, in the backwards direction, hydronium would be giving away the proton to form water. It's also an acid. Now, the language that we use is we call the product acid a conjugate acid. If we run the reaction backwards, chloride will be accepting the proton to become HCl, right? So chloride is also a base. And to designate that it's the product base, called the conjugate base. Now, every acid gives away its proton, forms a conjugate base. And every base, when it accepts a proton, forms a conjugate acid. So evaluate this one. What's the acid? What's the base? What's the conjugate acid? What's the conjugate base? Okay, so HCl becomes chloride. What does that make the HCl? The proton gets transferred. That makes HCl the acid. And the product that's formed after it gives away the proton is the conjugate base. Ammonia accepts the proton, which makes it the base. when it accepts the proton, it becomes the conjugate acid. Okay. The language that is used to talk about this process is different than maybe you've heard before. So chemists talk about acid-base reactions as proton transfers. So they might say the proton is transferred from the HCl to the ammonia.
I guess I'm a little confused because if a base is a proton acceptor, then why in this situation is NH3 giving hydrogen to NH4?
It's not. It's taking this. You mean when it goes backwards? Ask the question again.
So just based off of what on the last slide, it said an acid is a proton donor, a base is a proton acceptor. So it's just kind of confusing to me that NH3 is the base when it looks like it's giving the hydrogen.
Okay, it starts with 3 hydrogens. We have here 4. So it had to accept 1 to get to 4. That makes sense. It had to take it in order to form the ammonia. Okay, which makes the ammonia the base. Get to the product, that product could reform the ammonia. The NH4 could donate a proton to the chloride to reform NH3. Something that is confusing to students is that, of course, chemists always have 4 different ways to draw things or write things, right? Okay, and that's true for acid-base reactions as well. One of the things that confuses students often is that not everything that's in the reaction always matters. And that's particularly true for counterions. When we build a chemical reaction, if we're actually doing it on the benchtop, we have to walk over to the chemical shelves and pull off the bottle that has the chemical in it, right? And that bottle has to be a substance that is electrically neutral. So for example, sodium hydroxide, when you dissolve sodium hydroxide in water, what happens? No, ionic substance, very, very soluble. So aqueous sodium hydroxide is actually Na+ and hydroxide ion. And the same thing is true for sodium chloride. It's actually, because it's aqueous, Na+ and Cl-. So what we actually have here, HCl and chloride and Na+ and hydroxide, there's some overlap. The ions are on both sides of the reaction, right? If they're on both sides of the reaction, do they matter? Like, are they actually involved in the reaction? Really? So what we're actually tracking here, assuming that HCl dissolves to form H+ and chloride, which is questionable. What we're actually, the change that we care about doesn't necessarily involve all of the counterions. Or we call the ones that are just there to make things electrically neutral, we call them spectator ions. They don't actually matter. And so sometimes we leave them out. A net ionic equation is one in which you just leave out all of the counterions that don't matter. So sometimes you'll get a question that says, you have a solution of sodium sulfate, for example. Sulfate matters because it's a base. The sodium ion doesn't matter. It's just a floater. It's just in there to make things electrically neutral, so you get to ignore it. Spectator ion. Okay. Helpful if you know from the formula what an acid is going to be, right? Now, in Chem 105, we told you that formulas were supposed to be reported in a certain way.
Repeat that question.
Okay, if you're writing a chemical formula, particularly for a covalent compound, what's the order of the letters?
Alphabetical.
It's typically alphabetical, right? The exception is organic chemistry molecules, where they write the formula in a way that tells you how the carbon chain is connected. But in the absence of that, you do it alphabetically. Okay, so why would this be written HCl instead of CLH? because it's an acid. When you see the H written first, it's not in alphabetical order, that's a clue. And the clue is that's an acid. So here's some examples: HCl, H2S, H2SO3. Those are written, the H is first because it's an acid. So if you see the H first, and it's not an organic compound where it's H3Cs, whatever, then you know that it's an acid. Okay, the other kind of acid that we see a lot are organic acids, or also called carboxylic acids. And that is some kind of organic molecule that's a carbon chain. And at the end of the molecule, the formula is written COOH. That corresponds to a certain functional group called it's a carboxylic acid group. So if you ever see something written COOH or sometimes CO2H at the end of a molecule, that's an acid. You've actually encountered a lot of acids because anything that has a sour taste is an acid. So vinegar, lemon juice, tomato juice, lactic acid in fermented stuff, anything that's sour, it probably has one of these weak carboxylic acids. Okay, from a Lewis structure, how do you tell? Okay. I was going to go back and insert all the Lewis structures. What's the Lewis structure of H2S look like? How does sulfur bond? Where is it on the periodic table? Right below oxygen, right? So does that mean that it's going to bond the same way oxygen bonds? Mostly, yes. It can expand its octet in a Lewis structure and oxygen can't, so that's a difference. But this H2S, this looks just like a water molecule, except it has sulfur in the middle instead of oxygen. Okay, and this H2SO3 molecule, it actually, one of those oxygens, two of the oxygens are actually OH group. So you have an OH bond. Okay, from a Lewis structure, anytime you have a hydrogen attached to a highly electronegative atom, chances are that hydrogen is an acidic proton. So from the periodic table, what are some electronegative atoms that you should be looking for? So electronegativity just reflects the attraction that a given kind of atom has for electrons. What happens to the electronegativity as you go across a row? What happens to electronegativity as you go down a row? It goes down. Okay, so what should the most electronegative atom be? Rule out the noble gases because they're not usually involved in bonds, so we don't worry about them. What's the most electronegative atom? Chlorine. What are some other very electronegative atoms? Chlorine, oxygen, nitrogen, sulfur, not so much. Okay. So anytime you have a hydrogen attached to something electronegative, and it should sort of be emblazoned on your soul, nitrogen, oxygen, chlorine, halogens. That's really what we see. Probably is an acid. And from a structural perspective, the CO2H group, carboxylic acids, the formula is going to look like this. What's missing that I haven't included in this structure? Lone pairs, right? So how many lone pairs does this oxygen have that aren't found? 2. How many are here? Also 2. Yeah. Okay, and what's a base that can accept a proton? If it accepts a proton, it has to make a bond to proton, which means it has to have electrons that can form that bond, right? So what are we looking for? Anything with a lone pair? Yeah. So if you draw the Lewis structure for this nitrogen, has a lone pair. There are lone pairs on these oxygens. There's lone pair on this oxygen. Anything that has lone pairs could potentially be a base. When something has a negative charge, like this hydroxide, why would that contribute to it being a good base? A positive charge to the neutral. Yeah, it wants to be neutral, right? It's destabilizing to have a negative charge. So if you can get rid of that negative charge, that's energetically favorable. So this hydroxide wants to gain a proton so I can get rid of the negative charge, which makes the hydroxide a good base. Okay. You have also had direct experience with bases in your life. Soap is mildly basic. That's why it feels slippery. And if you were ever, maybe none of you were as naughty as some of my children, but I have washed my children's mouth with soap. Or it tastes nasty. Why does it taste nasty? It's bitter, and that bitter taste is because something is a base. How many of you have ever spilled bleach on your hands? What does it feel like? Really slippery, and that's because bleach is a base. Okay, some more terminology. When we talk about acids and bases, we particularly describe whether it's a strong acid or a weak acid. And we talk about whether something is a strong base or a weak base. Okay. We also use the words dilute and concentrated, and those are not the same things. So strong does not mean concentrated, and weak does not mean dilute. Okay, tell your neighbor, what's the difference between concentrated and dilute? What does that refer to? So those terms refer to individual solutions. So a sample can be concentrated or dilute. And how do you tell the difference? If it has a lot of moles of material in it, it's concentrated. If it doesn't have very many moles of material, it's dilute. So concentrated or dilute just refers to the molarity. Okay. What does weak versus strong refer to? So there are definitions, standard definitions. We talk about acids being strong acids or weak acids. Now, Arrhenius said a strong acid is one that ionizes completely in solution. What he meant was, if you start with a strong acid, you mix it into water, according to the Arrhenius definition, you get a lot of H+ and chloride. In fact, a strong acid, where does the equilibrium lie? Completely to the right. A strong acid, you get all product. Now, we use the word ionizes completely. That comes from the previous not so accurate Arrhenius model that assumes that you actually get ions necessarily that form directly from the acid. The more accurate Bronsted-Lowry model says, well, that isn't actually what happens, right? What actually happens is that the acid completely transfers its proton to the water. So the water acts like the base to form the hydrogen and the counter ion, the conjugate base of your starting atom. Okay, strong acid is one where when you mix it into water, it completely reacts with water to form the bromine. So if it's reacting completely, what kind of K values are we talking about? They're high, right? And in fact, the lowest K value I know for this reaction for a strong acid is 10. Most of the equilibrium constants for the reaction of strong acids with water are 100 or 1,000,000 or 1,000,000,000. Perchloric acid has a K value that's typically reported as large. That's because it's on the order of 10 to the 23rd. So how much starting material do we have left when we mix strong acids into water? Not very much. You know from Unit 2 that there still has to be a little bit, but for all intents and purposes, within the concentrations that we deal with and the significant figures that we have, can we assume that a strong acid, you have complete conversion of starting material to product? Yeah. Okay. What are the delta G? What's the sign of the delta G naught values for the reaction of strong acids with water? Negative. Absolutely. And some of them are hugely negative. Okay. What do we know about the delta G values? If we start with no product in solution and we're just dissolving our starting acid in water, what's the sign of the delta G values? All negative, right? Because if you start with all starting material, the reaction can only go forward, so the delta G is negative. So we're dissolving strong acids in water, both delta G and delta G naught values are negative, assuming that we don't have a lot of other stuff in there. Okay, so if strong acids ionize completely, equilibrium lies all the way to the right. What's a weak acid? Without looking at the slide, you could have figured that out, right? A weak acid is one that doesn't ionize completely. So where does equilibrium lie? Equilibrium lies on the side of the starting material, where equilibrium lies to the left. What kind of K values are we talking about here? Small, how small? Most weak acids have K values for the reaction with water that are 1/100th, 0.01 or less. And most weak acids are on 10⁻³ 10⁻⁵. Farther down. Okay, so if the K values are all less than 1, what's the sign of delta G naught for weak acids reacting with water? Positive, yeah. How about the delta G values? Do they have to be positive too? It depends on the actual concentration conditions that you have. If I start with pure water and dump in a bunch of my weak acid, what's the sign of delta G when that reaction starts? It's going to be negative because we start with a Q value of 0. So even though the equilibrium lies sometimes far to the left, we're still going to proceed forward a little ways before the reaction stops at equilibrium. So delta G can be negative or positive, depending on what we start with. Okay. A student asked, how do thermodynamics and kinetics apply to acid-base reactions? Is there any of Unit 2 that doesn't apply here? Applies here. How about the kinetics? Okay. How high do you think the energy of activation is for transferring a proton from an acid to a base? Is there a big energetic barrier for that proton to just kind of lower? It's low. So the energies of activation are low. So what does that tell you about the rate constants for acid-base reactions? They're pretty high. Yeah. So what does that tell you about the half-lives for acid-base reactions? Really, really small. In fact, for these reactions where you mix an acid into water, by the time you have it mixed, it will already have come to equilibrium. So these are really, really fast reactions. We don't even actually worry about the kinetics of acid-base reactions because for all intents and purposes, as far as we can tell, they happen so fast, they might as well be instantaneous. Very, very fast reactions. Okay. So tell your neighbor the difference between a weak acid and a strong acid, and then I'll tell you 4 or 5 different ways that chemists say the same thing.
Strong acid is one
Okay, so these are different ways chemists will say it. A strong acid is completely ionized in water. A weak acid isn't. Strong acids will completely dissociate in water. Is that the same thing as ionizing? Yeah, weak acids won't do that. A strong acid will be completely deprotonated in water. A weak acid won't. What does that mean, deprotonated? It got rid of its proton, right? A strong acid is better at giving its proton away than a weak acid is. A strong acid is more likely to donate its proton than a weak acid is. So these are all ways that chemists use the language of acid-base stuff, and they all mean the same thing. But because chemists speak a language just like English or Spanish or Portuguese, not every chemistry speaker uses exactly the same words. Okay. If we're going to compare the strength of acids, we want a number, right? Because of course, physical chemists always want a number, and they like tables of data. I want to find all those tables of data for delta G and delta H naught and all those things. Well, when we get to acid base, we're going to have a table too. So if we want to compare the acid strength, what we do is compare the acids under the conditions that we typically use them. And we typically take an acid and make a solution in water, right? So what we see is that an acid, an HA is code for any generic acid, will react with water. The acid will donate its proton to water, so we'll be left with the conjugate base of the acid, which we call A minus, and hydronium. We could take that reaction and write an equilibrium constant expression for it. Okay, so we have the concentrations of the products, A minus times hydronium ion, divided by the concentration of the starting material, HA. Why doesn't water show up in that? Water's the solvent, so we assume that it's a pure liquid. So its activity is 1, so it doesn't have to show up in the equilibrium expression, which is nice. Okay, because we use a lot of these reactions for different acids, they have their own name for the equilibrium constant, and we call it Ka. What does A stand for? Acid. In words instead of symbols, we call that the acid dissociation constant. Okay. Tell your neighbor how to correlate the size of the Ka value with the strength of the acid. Okay. The farther the equilibrium lies to the right, the higher the Ka value, right? Stronger acids have an equilibrium that lies farther to the right. So the stronger the acid, the higher the Ka value. Here we have a table. This is actually the table that shows up on your back of your exam and that we use over and over again. It's just a useful one. There are lots of different versions of a Ka table. There is a 5-page Ka table in the back of the Gilbert textbook. It's organized alphabetically, which is different than this one, but lots of information. Okay. You can see from the headings, the acids over here. By the way, what other useful information does this table have? It has the names and the structures of all of the polyatomic ions that you don't remember the formulas from Chem 105, right? And they're all here. So what does that mean about whether you actually need to memorize those for the rest of the class? They're all here. Okay. Tell your neighbor how you can tell if these are the acids. How does the formula tell you that they're acids, even if it didn't say acid above it? All of them. First in the formula, or COOH or CO2H backwards here. What do you notice about most of the bases? They all have negative charges. Yeah. That's common. Okay. Examine the Ka values in the table and tell me why the acids and bases are in the order they're in. How's the table organized? Look at the top. The largest Ka values are at the top, and as you go down the table, the Ka values diminish. So where are the strongest acids? Top. And then what happens to the acid strength? It goes down. Okay, why is there no K value listed for hydronium ion? What would this reaction be? So all of these are for the reaction of that acid with water to form hydronium. plus this conjugate base. Or this hydronium line. Hydronium reacts with water to form water plus hydronium. What's the K value here? 1, which is why it isn't shown. Okay, so where are the strong acids on this table? The top, everywhere above hydronium are strong acids, everywhere below is weak acid. That. Okay, tell your neighbor how to read the table. And tell your neighbor what reaction the K value in this table correspond to.
She was saying that.
Reaction that the table is trying to depict. Suppose we start with perchloric acid. HClO4 is reacting with water, so the water part isn't shown on this because these reactions are all with water. To form the conjugate base, which is what shows up on the base side, perchlorate, plus ammonium. You can take any of the acids on that table and just substitute the acid and the conjugate base. Okay, so why does the hydronium line with the line, why is the K value 1 there? So if we start with hydronium, reacting with water, what's the conjugate base of hydronium? Water. When water accepts a proton, we form hydronium. Why does the K value have to equal 1 here? We have the same things in the starting materials and products. So the K value has to equal 1. Okay. Now something to keep in mind is what makes a strong acid strong is that the back reaction almost doesn't occur, which tells you that the conjugate bases of these strong acids are really unreactive. In fact, they're so unreactive that they don't essentially react backwards. They might as well not be bases at all. They're kind of useless. This is where the language gets fuzzy, because chemists refer to these as weak acids, or weak bases, or very weak bases. And what they really should be calling them is abysmal, useless, worthless bases. Okay, so the conjugate bases of strong acids are unreactive as bases. Okay. Then everything that's the conjugate base of a weak acid is also called a weak base. But are they as weak as those? The conjugate bases of all of these weak acids, everything below water, those are bases that actually are fairly reactive. We don't call them strong bases because when they react with water, equilibrium doesn't lie all the way on the side of the product. But are they the same strength of bases? What happens, so the acid strength goes down as you go down the table, right? What does that mean about the base strength as you go down the table? The bases get stronger. Yeah. So acid strength falls as you go down the table, but the base strength increases as you go down the table. And those bases will still react with water. Okay. So a student said there's many different kinds of acids. How do you remember and differentiate between them all? Only thing you need to know is their Ka value. Your Ka value will tell you Is it a strong acid? Is it a weak acid? If it's a weak acid, it will tell you how weak the acid is. And that's really all you need to know to analyze. Okay. If the Ka value is what we use to talk about whether something is strong or weak, does that mean that chemists go around saying, well, the Ka value is 5.342 times 10 to the minus 11th? Mouthful, right? And so chemists who like to cheat and write and talk in ways that are shorter, have you noticed this? They have a code that allows them to talk about the strength of the acids and the Ka value while not having to talk in scientific notation. What they do is they take the Ka value, they take the base 10 log of it and multiply it by -1, which allows you to come up with an easy number. So let me give you an example. Take the Ka value for acetic acid, which is vinegar, is acetic acid. It's 1.8 times 10 to the minus 5th. How would we calculate the Ka value? Take minus base 10 log of 1.8 times 10 to the minus 5th. You get a number that I think is about 4.6. The calculator gives you 4 point something else. That's fine. Okay. Why is this negative sign in here? Most of the pK values that we talk about when we're comparing are for weak acids. And those all have Ka values with negative exponents. So we put the negative in front so we don't have to talk about the negative exponent. Okay. So what does that mean? It means that you can use the sign and the magnitude of the pKa to tell you how strong the acid is, just like you can. Okay, so tell your neighbor, why do we have to use pKa's if we already have the Ka value? Why did chemists come up with that? It's just easier to talk about. Why do smart work questions like to use pKa instead of Ka? The smart work always wants you to do more transformations for every problem, right? So sometimes will they give you the pKa when what you need is the Ka? Often.
So what is the range of the pKa values? Oh,
Good question. What is the range of the pK values? Okay, so strong acids all have a Ka value greater than 1, right? Which means that strong acids, according to the math, Ka value is greater than 1. Take the base 10 log of a number greater than 1. What's the sign of that number? It's positive. It's actually positive. So it, either base 10 log or natural log of a number greater than 1 is positive. Eventually, logarithms tell you how many digit decimal places you are away from 1. So if you have a K value that's 100, you're 2 decimal places away from 1, right? 2 factors of 10. So your pK is about 2. Okay, but because we have this minus in here, a strong acid with a K value of 100 has a pK of -2. So strong acids have negative pK values. Weak acids have positive pK values. So the pK pretty much tells you, has the most information about the exponent in there. Okay. So for this Ka value, it's somewhere around 10 to the minus 5, which means your pKa is somewhere around 5. So the larger the negative exponent in your Ka, the larger your positive pKa. The weak acids have positive pKa's. And the weaker the acid, the larger the positive pKa, because that would correspond to a negative exponent in your Ka value. So sometimes, instead of reporting a Ka table, we also have pKa tables. Now, pKa tables typically are only reported for weak acids. That's what we see here. How do you know these are all weak acids?
positive.
Because they all have positive. Yeah, absolutely. Is it still organized the same way from stronger weak acid to weaker weak acid? Yeah, it is. So it's pretty much done the same way. You will have a copy of this pKa value on your exam as well to use. And there's a lot of overlap between the Ka table that you're going to have and the pK table, but there is some differences in. Okay, so tell your neighbor how to read the numbers for Ka and pKa to tell you whether it's a strong acid or a weak acid. If you can do it without me putting it on the slide, and then I'll put the slide up and you can check your thinking.
Higher.
Then reverse the check.
It's strong.
Okay. These ideas connect to unit 2, right? Strong acids have what kind of delta G naught value? Negative. So a strong acid would have a high Ka value, a negative pK value, and a negative delta G naught value. Okay, weak acids. What kind of Ka value do they have? Less than 1. What kind of pKa value do they have? Positive. And what kind of delta G naught value do they have? So what kind of delta G naught corresponds to a K value less than 1? Positive. Yeah. Exactly. Okay. Because chemists love to measure and compare, we also can do the same thing with bases. So just like we have a Ka value that corresponds to where the equilibrium lies for an acid reacting with water, we can also take a base and react it with water and come up with an equilibrium constant. Now, notice what's happening here. The base is a proton acceptor, right? Where's it getting the proton from? Water. So in this reaction, water is acting as an acid. So the base takes a proton from water, the conjugate acid of the base, and the conjugate base of water. Okay. And everything that we do with Ka, we can also do with the Kb value. So we can take the pKb value. And the same trends exist. So the stronger the base, the higher the Kb. What does that mean about the pKb? Yeah, the stronger the base, the larger the Kb value, which means the more negative the pK value. The weaker the base, what happens to the Kb value? Smaller it is, which says what about its pKb value? The larger the positive pKb. Okay, and our tables often have pKb value as well as pKa value. Notice anything? So as you go down the table, what happens to your acid strength? It goes down. As you go down the table, what happens to your base strength? It goes up. Is that what should happen? Yes. The weaker the acid, the stronger the base, the conjugate base is that formed. What else do you notice about the actual numbers for pKa and pKb? What do they add up to? Always add up to 14. So if you know the pKa, is it easy to calculate the pKb? Yeah. Okay, what else does that mean? If you know the Ka, do you know the pKa? You can figure it out easily now. Right? If you know that, do you know the pKb? Yeah. So does that mean you also know the Kb? Yeah. So all those things are related. Okay, please keep in mind that there's lots of possible acid-base reactions, and the Ka and the Kb values only apply to reaction of the acid or base with water when you mix it into a solution. So it's a very specific reaction. anytime you dilute an acid or a base in water, have the reaction with water occurring, the Ka and the Kb are going to apply. Okay, but if I mix an acid and a base together and they're stronger than water, those will react instead. We'll go there a little bit later. Okay, you guys probably need a break, right? Yeah, why don't you take a 5-minute break?
Like Wednesday night, I was like. I don't have also kind of like the latest. There's always like, I never do it until Wednesday night. Oh, never. It's the one that actually do it. I was hustling.
Conjugate base with water.
I just.
That would correspond to the K. Okay. So you're right, that if you have an acid, HA plus water goes down. The reverse of that would be like
Yeah, and so my alarm's not.
B is for reacting.
What the kids do.
Conjugate base.
I'm kind of right, like I was like just
Different reaction. Question.
Oh, okay, sorry. It's okay though.
Conjugate. Yeah, and those are two different reactions.
Yesterday.
Oh, this is peaceful.
It's just floating.
Yeah.
Changes, change your dimensional analysis essentially.
Forget it. The concentration. You concentrate on volume that gives you the mole. The number of moles for with the number of moles you end up with. But that's just for the one stoichiometry.
Radius.
Okay, so what we're seeing is that stronger acids, when they give up their proton, they form a conjugate base that is less reactive and therefore weaker. Okay, so the more stable the conjugate base, stronger the acid is that formed it, the less stable the conjugate base, weaker the acid. And you see the trends by comparing to Ka. What do you notice about the Ka and the Kb values? Remember that the pKa and the pKb added up to 14? 14 is actually kind of a magic number here. What do you see about the Ka and the Kb? The Ka is 1. It's 10 to the minus 14. The Kb is 1. If you multiply the Ka and the Kb together, what do you get? Get 10 to the minus 14. 14 is the magic number. We'll come back to that. Did this one already? Okay. So look at the energy diagrams. Bring this back to what we did in unit 2, in some respects, unit 1. If we're reacting an acid, HA, with water, we're going to form a conjugate base and hydronium, right? Okay. Those two diagrams, one corresponds to the reaction of a strong acid with water and one a weak acid with water. Tell your neighbor why. Which is which?
Strong acid is a weak base, but it's stable. So that's why it's.
There's about 6 intellectual connections that I need you to make. Once you make them, it all makes sense. How you make it? Trying to memorize things. How well does that work in this class? Just memorizing things.
It doesn't work.
It doesn't work very well.
Yes. And that's.
Okay, this one. Strong acid or weak acid? Strong acid. How come?
Products favorite.
What's easier, the forward reaction or the backwards reaction? Forward reaction is easier, so in equilibrium, what are you gonna end up with? Forward product. So what would your K value be? Big. So this corresponds to reaction with strong acid. Okay, how about this? What's easier, the forward reaction or the backwards reaction? Backwards, so where will equilibrium lie? The left. So what kind of equilibrium constants, Ka values, are we talking about? Less than 1, yeah. Okay, so here's the connections. Whether something is strong or weak actually reflects the position of the equilibrium, right? Equilibrium lie to the right and how far, or does it lie to the left and how far to the left? And that depends on how good the forwards and backwards reactions are at actually occurring. Okay. If we have a very unreactive conjugate base, how good is the backwards reaction going to work? It's not, right? So if this conjugate base is unreactive, which happens when it's really stable, which happens when it's really low in potential energy, then what kind of K values are we going to have? That's too many links at once, right? Okay. Turn to your neighbor and explain what the stability of the conjugate base has to do with the Ka value. We react an acid with water. What does the stability of the base have to do with the K value?
Stronger acid.
Those higher are likely to react more.
Stronger acids if the stability is higher.
Is accepted as well.
I was gonna accept it.
A bunch of connections. They all fit together in a beautiful little circle. Okay, when the conjugate base is lower in potential energy, that means it's more stable, right? When it's more stable, is it happy and not reacting? Yeah. High stability actually corresponds to low reactivity. So when the conjugate base is more stable, conjugate base is less reactive, which makes it what kind of base? A weaker base. A weaker base is less likely to react backwards to reform product, right? So a weaker base is going to result in less back reaction, which means equilibrium will lie more on the side of product, right? So anything that makes the base more stable does what? Makes equilibrium lie more on the side of product, which means the equilibrium constant Ka does what? Goes up. Which means what about the strength of the acid? Stronger acid. Okay, one more time, see if you can explain that, even if it's just writing it down on your paper. It will help you a lot to have made all those connections and have them feel natural.
Is that because like the strong acid basically like makes the proton less? So it's just like.
Yes, yes. So the more stable the conjugate base, the less it cares about not having the proton. Happier to stay as a base.
More stable, less reactive.
Okay. Does that mean that for a given acid, we can figure out what the conjugate base would be and then examine the structure to decide whether we think that's stable or not and use that to predict how acidic the starter acid is? It does. So we have these Ka values, right? Will you have every possible Ka value in front of you to compare the acidity of different molecules? You won't. Sometimes you have to just guess at whether something is more acidic or less acidic.
On the test.
Not necessarily.
Oh, no.
On the test, I could give you different molecules that there aren't a Ka value and ask you to rank their acidity. Actually, it's totally doable. There's a handful of rules that you follow, no problem. Okay. So here are the rules. The more stable the conjugate base, the more acidic the precursor acid, right? And there's a handful of things that stabilize the conjugate base. Most conjugate bases are negatively charged, right? Do you remember from Chem 105 when you were ranking the stability of different Lewis structures that you always wanted to get rid of charge if you could, right? Do you remember? Do you know why? Because the actual charge itself destabilizes the molecule. Okay, so it's the negative charge in the base that is unstable, that lends itself to being reactive. Anything that stabilizes the negative charge makes the base less reactive, which makes the precursor acid a stronger acid. Okay. And there's some things that you already know that make sense that could stabilize the negative charge in a conjugate base and thus influence the reactivity of the precursor acid. So electronegativity is a measure of how much attraction for electrons something has, right? Okay. Something with a negative, how do I phrase this? If I have a negative charge on oxygen, how well does oxygen tolerate a negative charge? If we look on the periodic table, oxygen is the second most electronegative atom. Can it decently handle a negative charge? Yeah, And you saw lots of negative formal charges on oxygen when you did Lewis structures in 105, because oxygen is very electronegative, and compared to other atoms, it can handle a negative charge. Okay. So if you're comparing two different conjugate bases, the first thing you do is look for where's the formal charge. If you're comparing a base with a charge on oxygen versus a charge on nitrogen, where will the charge rather be? On oxygen, because oxygen is more electronegative. Okay, which means if we're comparing this base, the amide base, to the hydroxide base, which one is a weaker base? Make the connection. The negative charge is better handled by oxygen than nitrogen. That means hydroxide is more stable. This means it's higher. Hydroxide is more stable, so it's lower in potential energy, right? And amide doesn't handle the negative charge well because it's on nitrogen, which makes it higher potential energy and less stable. Okay, what does that mean about the strengths of the bases? The more stable structure is the weaker base, which means its conjugate acid is stronger. So HOH would be a stronger acid than NH3. Okay, we're gonna do some more examples about that. But the first thing you do is say, where does the charge go? Okay, now in Chem 105, briefly drew different resonance structures, and we talked about resonance stabilization. And that was the last you heard about it in 105, and it disappeared out your ears and you didn't think about it at all, right? Here is an example of where it's relevant. I can take two different bases, different conjugate bases, with a negative charge on oxygen. One of them could be resonance stabilized. Negative charge is spread out by resonance, and one, the negative charge, there's only one resonance structure you can draw, so the negative charge is stuck on a single oxygen. Does that make a difference? It does. If the negative charge can be spread out by resonance, what happens to the stability of that base? Stability goes up. What happens to potential energy? It goes down. What happens to reactivity if the potential energy goes down? Reactivity goes down. So what happens to base strength? It goes down. So what happens to the strength of the acid that would have given you that conjugate base? It goes up. And what happens to the Ka value for that acid? It goes up.
When you say reactivity, you mean reactivity going to the base?
Yes, reactivity. Well, I meant reactivity of the base to go backwards.
Oh, okay.
That probably helps.
Yeah.
Okay, there is a concept that you have not seen or heard yet, unless you're one of the small subset of people that have already taken 351. I need you to come up to the front of the class and do the eyebrow thing. So Josh in the back has had 351.
I haven't, I just did the eyebrow thing.
That makes more sense. Okay, so there's a thing called induction, where if you have a negative charge on an atom, if there are other electronegative groups that kind of surround it, some of those electronegative groups pull some of the electron density away from that position, which acts kind of the same thing as it's almost like it makes the charge less and it stabilizes. Let's do some examples. Okay, let's right on the a really clear example of the difference that electronegativity makes is to compare the acidity of versions of the elements in the second row. So we have methane, right? It has some protons, some hydrogens. Potentially, those could be acidic protons, right? Okay, if we go one over on the periodic table, we get to nitrogen. For ammonia, right? One more over. We can form water. One more over. Get hydrogen fluoride. Okay. Those have different, those protons, each of those molecules have dramatically different acidities. And we can visualize that by saying, what's the stability of the conjugate base it would form when that putative acid loses a proton? So if we take methane, if that's the acid, what does the conjugate base look like? So we're going to pull off a proton and leave the electrons in the bond behind. It would look like that, right? How well does carbon tolerate a negative charge? Not very electronegative. This is called a carbanion. It is super reactive. In fact, I've worked with these a little bit. You can do some chemistry synthetic reactions where you can actually make this and use it as a component of a reaction. And you have to do it in a specialized system where it doesn't get exposed to air, because it will react explosively with the water vapor in air and it will actually explode. What does that say about how reactive it is? Very reactive. So what kind of base is this? Strong base. Okay. From the slide, pK value is approximately 48. So what would the Ka value be for methane to donate its proton? Something on the scale of 10 to the minus 48. Not very acidic, right? Okay, if we go one over and we look at nitrogen. When nitrogen loses its proton, form amide, which is negative charge. So what do we know about the electronegativity of nitrogen versus carbon? It's more electronegative, right? So what does that tell you about how well this nitrogen is going to tolerate the negative charge? A lot better than carbon, right? Okay, so what do we know about the stability of the conjugate base compared to the carbon? It's more stable. So what does that say about the reactivity as a base? It's less reactive, which means it's not going to back react quite as much. So the equilibrium will lie a little more to the side of this. So what does that say about the acidity of ammonia? Higher. It's still, remember, I'm thinking of from the top of my head what the pKa value is. So I might be wrong. It might be a little bigger than this. Is there a big difference in these pKa values? Yeah. How strong a base is this? So if the pKa value is 18, what's the Ka value? Okay, how acidic is ammonia? Not very. Okay. What about water? Pull the proton off of water. Form hydroxide ion with a negative charge. Oxygen is substantially more electronegative than nitrogen. How well does that tolerate the negative charge? Better. Okay, so what does that tell you about the reactivity of this hydroxide? It's going to be more, it's more stable, therefore it's lower in potential energy, therefore it's happier to stay there, therefore it's less reactive than what is up here, right? So what does that say about the acidity of water compared to ammonia? It's going to be more acidic, and in fact, pKa for the reaction of water with water is 14. What's the Ka value for this? The Ka value is 1 times 10 to the minus 14. This is actually a special Ka value that we call W. Okay. And fluoride. If we pull off the proton, what do we get? Fluoride ion. How well does fluoride handle a negative charge? It's the most electronegative atom, so it handles it really well. So if you think a pK value is for this? You know, it's gonna be a lot smaller than 14. Okay, so Matthew says he's expecting that HF is gonna be a strong acid. So if it's a strong acid, what kind of pK value would it have? Negative. Because that would correspond to a Ka value greater than 1. Actually, hydrofluoric acid is a weak acid. It has a pKa, and I don't know for sure what it is. About 2. It is 10 to the minus 2. That feels counterintuitive, right? Fluoride should handle the negative charge really well. And that has to do with the size of fluoride ion. How big is the fluoride ion? It's really small. If you take a negative charge and you concentrate it into a small area, what happens to the potential energy? It goes up. It has more impact if you squish the negative charge into a small location. And so because fluoride is really small, what that means is actually not as stable as you'd expect based on electronegativity. So here's the image to think about. How concentrated the negative charge is in space? Why does that make a difference? When you were 8 years old and your mom was trying to teach you to sweep the kitchen floor, or however old you were when you first learned how to do that, one of your parents would hand you a broom and a dustpan and say, go to work, right? And you'd sweep, and then you sweep the stuff into the dustpan, and then you lift the dustpan up, and what do you see? Stripe. Okay. What did you do?
Whale and its teeth.
So
The other-
if you were, that's a good way, turn it around and go the other way. If you're really good, you would just keep on working on it. But chances are, once in your life, what did you do instead?
No.
When you take that dirt and you squish it and concentrate it into a small space, it has more impact, right? When you spread it out, it doesn't matter as much. Same thing for charges. If you squish the charge together into a small location, it has more impact, the potential energy is higher, and it's more reactive. So fluoride, because it's very small, it's a difference. It's not as strong as you would think. That's why resonance works too. When you have a negative charge and you spread it out by resonance, what are you doing? Instead of keeping that negative charge in one place, you're spreading it out over multiple locations. It's like taking that little stripe of dirt and spreading it out. Okay. Electronegativity makes a lot of difference. Depending on the size, it doesn't make as much difference as you might expect. Here, let me put back on the screen. We're comparing methane versus ammonium as our acids. Which is stronger? Pull a proton off of methane, what do you get? You end up with a negative charge on carbon. If you pull a proton off of ammonium, what do you get? You have a negative charge? You have a neutral substance. Okay. So what's more stable? A neutral substance formed when you pull a proton off of ammonium or when you pull a proton off of methane? Ammonium, the conjugate base of ammonium is way more stable. So which one of those is a stronger acid? Ammonium. Okay, NH3 versus NH4 plus. You pull a proton off of ammonium, you get ammonia. You pull a proton off of ammonia, you get NH2 minus. What's more likely to happen? Yeah, you're gonna pull a proton off of ammonia. Let's another one. Okay. Resonance is difference. So which do you think, what do you know about this CO2H group? Which proton is going to be the one that is most likely to be donated?
One of the oxygen.
The one here, right? You know that because when you pull the proton off, you want the negative charge on oxygen. Okay, how about over here? Which proton is going to be donated? Also the one on the OH group. Okay, but notice this. The pK for this, for acetic acid, is 4.8. I said 4.6, so. Okay. The pKa for an OH on ethanol is 17. So that means the Ka value for this is about 10 to the minus 5. The Ka value for this, or that proton, is about 10 to the minus 17. Is that a big difference in acidity? Ah, it's huge. Well, that comes down to how concentrated the charge is. If you pull the proton off of the OH for ethanol, you end up with this structure. Any resonance structures possible that are stable? This is all we get. So this negative charge is stuck on this one oxygen. We pull the proton off of here, we end up with this structure, right? But really, it has a resonance structure that looks like this. So where's the negative charge? It's really only half a negative charge on each of the oxygens because the actual molecule is both of those at the same time. So resonance spreads out the negative charge, which gives it less impact, which lowers the potential energy and increases the stability and makes this way less reactive as a base, makes it a much weaker base, which means it's a stronger acid. Is it a big difference or a little difference? It's a huge difference. Resonance makes a huge difference. Okay, one more. This is the one you haven't seen before. Okay, how do I describe this? From Chem 105, what do you know about the electron cloud surrounding a molecule? Are electrons really individual lone pairs? No. Where's the electron really? Multiple places at once, it exists in a molecular orbital that's essentially a cloud of electron density, right? So if we have, for example, hydrogen fluoride, what it actually looks like hydrogen nucleus, and a fluorine nucleus, surrounded by a cloud of electrons. This bond, polar and nonpolar. There's essentially two electrons in this bond if we draw it as a Lewis structure, right? What we actually have is a whole cloud of electrons around the fluorine and the hydrogen. Where are more of the electrons? They're pulled more towards fluorine. What we actually have is a polar molecule where more of the electron density belongs on one side than the other, right? Okay, now suppose so take the idea that if you have some electronegative stuff at one end of the molecule, what's going to happen to the whole electron cloud? It's going to suck a little bit more towards the more electronegative things. Okay, now compare the acidity of different bases. Okay, we call these the hypohalous acids. This is essentially water, except that one of the hydrogens in water is substituted with halogen, right? How come we can do that? Hydrogens only bond to one thing. All of the halides, fluorine, chlorine, bromine, iodine, how many things can they bond to? One. Okay. When we form the conjugate base by pulling off the only proton, what does it look like? We're going to form conjugate bases. All of them have the negative charge on the oxygen, right? Okay, So we can't rank those different acids in terms of acidity based on where the negative charge is, whether it's on a more electronegative atom or not, right? Because they're all on oxygen. Any resonance structures? No. Okay. But what has more attraction for electrons, chlorine or bromine or iodine? Chlorine is a lot more electronegative than the other two. And iodine is hardly electronegative at all. Okay, what's the presence of that chlorine going to do to the negative charge on the oxygen? It's going to pull a little bit of it away to bromine and iodine, which means that for all intents and purposes, there's not as much charge on the oxygen when it's bonded to chlorine compared to when it's bonded to bromine or iodine. So what happens to the acidity? Here's my. Okay. What happens to the Ka value? Iodine is 2.3 times 10 to the minus 11. When you put a chlorine in there instead, what happens to the Ka value? Changes by about 1,000-fold, right? Presence of the chlorine, well, this is compared to the iodine, is 1,000 times more. Can it make a big difference if you have something else electronegative that's not even bonded to the negative, to where the negative charge is? It's just floating close to it in the molecule. Does that make a difference? Induction. So if there are electronegative groups that are close to the negative charge, that pulls some of the negative charge away, stabilizes the conjugate base. What the precursor acid? More acidic. Okay. So the three things that you normally have to worry about are, tell them to me, electronegativity of the atom that bears the charge in the conjugate base, presence of resonance stabilization or not that could stabilize the negative charge in the base, or induction that could pull away some of the negative charge on the base. Sometimes things aren't the way we would expect. So within a family, the numbers don't match. So HF, let's see, change the camera. HF, HCl, HI. Based on electronegativity of the atom that bears the charge, what should be the stronger acid? What should be? On an actual Ka table, rank the Ka values. I dramatically higher. HF. In fact, HF is a weak acid. The rest of these are strong. So what's happening here?
Does that have to do with the size of the atom?
That has to do with the size of the atom here. So if we're comparing conjugate bases where the atom that bears the charge is within the same family, then it's not just electronegativity that we have to consider, it's the size of the atom. And then we choose the atom that is the smallest, and that's the least stable. So hydrogen iodide is more stable, is more acidic than HCl, which is more acidic than H. Okay, water versus hydrogen sulfate. When you form the conjugate base of water is hydroxide. Conjugate base of hydrogen sulfide is sulfuric acid. You get hydrogen sulfide. Okay, based on the electronegativity of the atom that bears the charge, which of these acids ought to be the most strong? Oxygen is above water, oxygen is above sulfur on the periodic table in the same family. So oxygen is more electronegative than sulfur. Just based on electronegativity, negative charge on oxygen ought to be more stable than charge on sulfur. What do you know about the size? Sulfur's bigger. How come sulfur's bigger? It has the same effective nuclear charge, but its valence electrons are in a higher energy level. So you've essentially added an extra layer of electrons, which makes the electrons cloud bigger. This means the negative charge is spread out over a larger space. What does that do to the concentration of the negative charge? It goes down. What does that do to the stability of these two bases? Conjugate bases. Negative charge on sulfur is actually more stable than the negative. When we're comparing negative charges on atoms within the same family, more stable conjugate base is the one that has the negative charge on the larger atom. That only comes up when we're comparing negative charges on different atoms in the same family. Otherwise, electronegativity matters more. Okay. More terminology. When we make a solution of an acid or a base in water, you know about those solutions. Drink an acid solution of acid. That's the thing. You do drink solutions of acids all the time. Lemonade is a solution of citric acid. Orange juice is a solution of citric acid. Vinegar is a solution of an acid. So it's not the fact that it's an acid or base that makes a difference. Okay. If you put half a teaspoon of vinegar in a gallon of water, are you going to notice it? Not much. Okay. If I take out my vinegar from the counter, unscrew it, and swig it down, will you notice? You will notice, right? The concentration of the acid makes a difference. Okay, and it's not just the concentration, it's the strength of the acid. So acetic acid is a weak acid. You're not actually going to get that much hydronium in your bottle of vinegar from your cupboard, right? But still enough to burn your throat going down. So we need a way of describing how much hydronium is in a given solution, because it's the amount of hydronium that's going to affect how that solution acts. And that way of reporting has to include, the amount of hydronium includes both the concentration of the acid and how strong the acid is, right? Because if I have a dilute solution of acetic acid in vinegar, that's not going to bother you so much. But if you have a dilute solution of perchloric acid, that's a whole different game. Okay, so we have to have a way that tells us how much hydronium is in the solution, that ignores what the acid, what kind of acid we actually have. Okay, so we need an easy way to communicate how much hydronium is. And we could just do a rice table calculation and get a concentration in moles per liter. And then if somebody asked you, you could say, well, there's 4.675 times 10 to the minus 11th moles per liter of hydronium. Is that a bit awkward? Verbally, it's awkward. Okay, so what are we going to do here? You're going to use pH, right? And you just figure out the hydronium concentration like you get from a rice table. And instead of reporting it in moles per liter with its scientific notation and all the exponents, we take the minus log of it to get the pH. Okay. There's some things you need to know to help you put this in context. Normal water, neutral water is pH 7. So that means a solution of water that isn't acidic or basic has a molar concentration of hydronium that's 1 times 10 to the minus 7. Okay, if you take the minus log of that concentration, you get pH 7. So pH 7 is neutral. If you have more hydronium than that, then this concentration is going to be higher, right? So what's going to happen to your pH value? So if the concentration goes up, what happens to your exponent? It gets less negative. So what happens to your pH value? It goes down. Okay. So if you have anything below 7 means you have more hydronium than neutral, or you have a solution that's acidic. So anything that has more hydronium in it than a neutral pH 7 solution is an acidic solution. And those occur at pH below 7. If you have less hydronium, that means it's less acidic or more basic. Anything that has less hydronium in it than 1 times 10 to the minus 7th molar, we call that a basic solution. That corresponds to pH values for that solution that are above 7. Okay. You're actually really familiar with solutions of a whole bunch of different pH. So if your water's pH 7, ocean water's about pH 8 because there's a lot of dissolved carbonate ion in ocean water, and that's kind of a base, so it raises the pH. Our water in Utah typically is above 7, a little bit basic.
It's crazy.
Soap is pH 10. It's fairly basic. That's why one of the reasons it's rise. Ammonia is pH 12. We regularly deal with things that are quite acidic. Vinegar is about a pH 3. Like the solution of vinegar that you buy at the store is 5%. 5% by mass solution. And it's about a pH 3. Your stomach is actually pH 2. What's the acid in your stomach? Actually hydrochloric acid. So you have a heck of a lot of hydrochloric acid in your stomach. Which is why when you have gastrointestinal distress, things burn in both directions. It's a whole bunch of HCl. Okay. So we have 2 minus log things. We have pH is minus log of hydronium and pH is minus log of the Ka value. How do you keep them straight and how are they different?
What I understand it is the pH is the solution itself, whereas the pKa is like the acid versus the.
Yes, so the pH tells you for a given solution with the concentration of the specific acid I have, how acidic is that solution. Okay, and the pKa just tells me what? How strong the acid is. So they're not the same thing. Okay, if we have pH, we can also have POH. Just like if you have a pKb, because you have a Kb because you have a reaction of a base with water to form hydroxide, we can also have a POH that corresponds to that reaction. Okay, both the pH and the POH and remember we talked about the magic number 14? The reason there is a magic number 14 for solutions of water is because water is a base and water is an acid. Tell your neighbor how from looking at the structure you know that water can act as an acid or a base. So in order for something to be an acid, you have to have a proton bonded to something that's reasonably electronegative. So water has hydrogen bonded to oxygen. That can make it acidic. In order for something to be a base, it has to have a lone pair, and water has that as well. Okay, so the Ka values are for a reaction of an acid with water to form the conjugate base and hydronium, right? If we do that reaction for water, reacting with water, we form hydroxide and hydronium. when you do the equilibrium constant, why is that the expression for the equilibrium constant? What happened to all our starter material? Are they both the solvent? So they're both pure liquids, so they don't show up in your equilibrium expression. So the Ka value for this reaction ends up just having the products in it. We call that the Kw. Okay, does this value show up on your Ka table typically? Do we see this reaction on the Ka tables that we show you? The Ka values that we show you on the Ka table that we're typically using only has Ka values greater than minus 14. So this doesn't actually show up, it's farther down on the table. Okay, so this reaction, I have my water bottle. Is it happening while I'm holding it? Yeah. So if I drink my water, am I drinking a little bit of hydroxide and a little bit of hydronium? Why doesn't that hurt me? Hydroxide's pretty reactive, hydronium's pretty acidic. How come it's not a problem? What concentrations do I have of those? If the K value is 1 times 10 to the minus 14, what kinds of concentrations do I have of those products of that reaction? In a pH 7 solution, which is probably close to the water that I'm drinking, the concentrations of each of those will be about 1 times 10 to the minus 7th molar. Am I really worried about drinking 1 times 10 to the minus 7th molar of something? Not so much, no. Okay. This has great implications for what's happening in solution because this is happening in every aqueous solution all the time. If I add, for example, some hydrochloric acid that reacts with water to produce hydronium, what happens to this equilibrium? So remember when we talked about solubility and the common ion effect? If you have 2 equilibria that share one of the products, are they going to influence each other? Yeah. So if I add acid to a solution, I'm going to produce some hydronium, right? So what does this do to that equilibrium? I just added product to this equilibrium. So I'm stressed the product side. What's going to happen? You shift the equilibrium. So what happens to the hydroxide concentration? If I add a bunch of a base to water, it's going to produce hydroxide, which is going to produce this. That's the common ion effect. We just stress this equilibrium. It's going to push it to the left. So what happens to the hydronium concentration? It goes down. So the amount of hydronium and hydroxide that you have in solution depend on each other, and they're governed by this Kw value. Okay, so if I have an acidic solution, that means pH is above 7. If the pH is above 7, that means the hydronium concentration is higher than 10 to the minus 7th, which means that my hydroxide concentration has to be lower than 10 to the minus 7th. Because the product of your hydronium and your hydroxide concentration in solution has to equal 1 times 10 to the minus 7th. Okay. In a basic solution, that means what are the pH values that correspond to a basic solution? Higher than 7, which means in a basic solution, my hydronium concentrations are less than 10 to the minus 7. Means my hydroxide concentrations have to be greater than 10 to the minus 7 because the product of the hydronium and the hydroxide concentration has to equal 1 times 10 to the minus 14. So the hydroxide and the hydronium concentration that you get always exist in relationship with each other. And anything that you do that changes the hydroxide concentration necessarily changes the hydronium concentration too, because they're related through the second equilibrium that's happening all the time. Okay. So there's always 2 equilibria happening in solution. If we add an acid to the water, you have an equilibrium of the acid reacting with water. But then you also have water reacting with water. If I add a base to solution, then the base is gonna produce hydroxide, and there's that equilibrium going on of the base reacting with water, right? But you also have water reacting with water, and the two equilibria are going to potentially interact with each other because of the common ion effect. Where the common ion, back to here, either hydroxide or hydronium. Okay. So what that means is hydronium concentration and hydroxide concentration in a given aqueous solution are always linked. They're governed by the equilibrium constant Kw. What's the W for? Water. Okay, so the reaction that occurs where water reacts with water to form hydronium and hydroxide, there's a name for that reaction. What's the name of it? Go back to it. This is helpful with your vocabulary. This reaction, the name of it is the auto-ionization of water. Why is it called auto-ionization? The ionization of an acid means to form hydronium, right? So normally when we talk about an acid ionizing, we're talking about it reacting with water to form hydronium. Is that happening here? It is, but it's water reacting with itself. So we call it auto-ionization. It's doing it to itself. So this reaction, water plus water to form hydroxide and hydronium, is called the auto-ionization of water, and it has a Kw value. Okay. Because of this relation, because of this reaction, there's some things that you need to know. One is expression for the Kw. Because of the Kw, if I take the minus log of Kw and simplify it, I get the pH plus the pOH equals 14. Okay, that actually has implications for the Ka and the Kb as well. If you multiply the Ka and the Kb, these are both solutions in water, right? The Ka and the Kb are for reactions that happen in water, which means that the Kw expression is always operating. Because of that, if you multiply the Ka and the Kb so the Ka has to do with the reactivity of an acid with water. Kb is the conjugate base of that acid reacting with water. If you multiply them together, you end up canceling things out here and there, and you end up with a Kw value. If you take the minus log of that expression, you end up with pK plus pK14. So remember when we looked at the pKa table that had the pK values and they all added up to 14? That's because of the second equilibrium that's happening all the time where water is reacting with water. Okay, we have a lot of equations, right? One of the challenges that I need you to surmount and into the ground is how to convert from one thing to another. Okay, remember in unit 2 when we would say K and delta G naught could be easily transformed from one into the other, right? So they essentially tell you the same thing. Acid base has easier transformations than that, but there's a lot of them. So if I know the hydronium concentration in solution, sometimes expressed as H+, but they're used interchangeably. Hydronium is more accurate. If I know that, how do I get to the pH of that solution? Well, I take the minus log of hydronium and I get that. If I want to convert from pH back to hydronium, well, hydronium concentration is 10 to the minus pH. Okay. pH and pOH have to add up to 14, right? If I know the pH, I can get to the pOH. The hydronium concentration is related to the hydroxide concentration, right? The product of the hydronium and the hydroxide concentration equals 1 times 10 to the minus 14. So if I know one, I can calculate the other. That's pretty straightforward. Okay, if I have the hydroxide concentration, I can get the pOH just by taking 10 to the minus, minus log of the hydroxide concentration. You should be able to do those conversions without having to think about it. Because will smart work ever give you the number that you actually need to work the problem? Of course not. It will always give you something else and make you transform it. Okay. make this connection to unit 2. When we are talking about the equilibrium of an acid diluted into water, can we just do a rice table? Figure out what your hydronium concentration will be? Yeah, and I'm going to show you some of those. Except when we talk acid base, nobody wants to know the hydronium concentration. They only want to know the pH. So if you're told the pH, that's just code for how you would get the equilibrium hydronium concentration. And if you do a rice table calculation to come up with the product, which is hydronium, you're going to have to convert it back into pH. Report it. Okay. So hydronium, the pH just tells you the equilibrium concentration of hydronium. Okay. Some equilibrium calculations. Take this back to what you already know. What's the pH of 0.1 molar HCl? Look at your rice table. Think this through here. We start with 0.1 molar HCl. We're putting into water, so what we actually have in the water is 1 times 10 to the minus 7th molar hydronium. Where does that come from? That's the value we get from the autoionization of water. Now, if we start with 0.1 HCl, do we care about this little driblet of hydronium that's already there? Within the significant figures, it does not matter. So most of the time, we pretend it's not there when we do our rice table. The problem on the recitation, and we're going to talk next week about what if you only start with a little tiny bit of HCl? Like if I start with 1 times 10 to the minus 7th molar HCl, do I get to ignore the hydronium from water? No. But most of the time, we're adding a whole bunch more acid than the amount that we have from the autoionization of water. So mostly our rice tables, we assume we start with 0. To all intents and purposes, we do. Okay, what kind of acid is HCl? Strong or weak?
Strong.
Strong. Now, in an exam setting or doing your homework, how would you tell? Pull out your Ka table, find HCl, and HCl is going to show up where? It's right at the top. It's above water, has a Ka value greater than 1. So what we do is we assume that it's going to react completely with water. As for the amount of significant figures that we typically have, that's really what's going to happen. Okay, so at equilibrium, we essentially have done a theoretically 100% yield reaction, right? Where we convert all of our starting material to product. So our hydronium concentration is 0.1. What pH does that correspond to? How many digits are we away from 1? 1. pH. 1. Yeah. Take the pH of 0.1, you get 1. Okay, so what's the POH? 14 minus 1 is 13. POH is 13. Now, have you learned any rules for significant figures with base 10 and natural logs? No. So this is what I'm going to have you do for pH. In the lab, standard usage, people have a pH meter that reports to 2 decimal places. So as long as you're reporting to no more than 2 decimal places, I won't take off significant figures. Okay. What if you have a base reacting with water instead of the acid? Sodium hydroxide is a strong base. You know what a strong base is. Really, the ones that you work with, the only ones you're going to see mostly are the that have a negative charge on nitrogen or hydroxide. And I'll show you next time how to tell, but hydroxide is a strong base. If hydroxide is a strong base, what are they going to do when it reacts with water? What does that mean about the Kb values? Kb value is 14 or higher if it's a strong base, which means that the Ka value for its conjugate base are 10 to the minus 14th or lower. Okay, essentially what that means is it's going to react completely to form product. So sodium hydroxide reacts with water. hydroxide. We have some sodium left over. If I start with 0.1 molar sodium hydroxide, do I end up with 0.1 molar hydroxide? This is essentially acting like an ionic compound dissolving completely. Okay, so what's the pH? What's the POH? POH is 1 because the POH is minus log of 0.1, so it's 1. So what's the pH? 14 minus 1 is 13. On an exam, how many you'd reported as 13.00 would be safe, right? Okay, so think this through. If the hydroxide, if the hydronium concentration at equilibrium that you get is 10 to the minus 2, you know, what's the pH? 2, yeah. If your concentration is 1 times whatever exponent, your pH value is just the minus value of the exponent. So this is pH 2. Okay. pH 2, what's the POH? 12. Okay. Is it a basic solution or an acidic solution? 7 is neutral, below 7 is acidic. So pH 2, how acidic is that? Very acidic. That's as acidic as your stomach acid. Okay. Hydroxide concentration. How did you figure it out? Can we say the hydroxide concentration times 1 times 10 to the minus 2 and 1 times 10 to the minus 14 and solve that way? We can. Can we say the POH is 12? So that means the hydroxide concentration is 1 times 10 to the minus 12. Yeah, you could do that too. Okay. Another one. Hydronium concentration is 1 times 10 to the minus 11. What's the pH? 11. Okay, if it wasn't 1, how would you figure out the pH? You have to actually calculate it in your calculator, because I don't know about you, but I can't do these 10 logs in my head unless it's 1. Okay. But it is 1 times 10 to the minus 11. So pH is 11. Is that a basic or an acidic solution? It's basic, which means the hydroxide concentration has to be higher than the hydronium concentration in solution. So if the hydronium concentration is 1 times 10 to the minus 11th, what's the hydroxide concentration? 1 times 10 to the minus 3rd. Get that because the product, when you multiply the hydronium concentration times the hydroxide concentration, has to equal Kw, which is 1 times 10 to the minus 14. Okay, so pH is 11, POH is 3. The hydroxide concentration, that 1 times 10 to the minus 3. There's more than one way to do it, but it all comes down to that little conversion table. You have time in your life to stop every time you have to do a conversion, look up the table and puzzle about how to do it. Life is too short for that. So these are easy conversions, get so you can do them without thinking about them. Okay. All the things I've shown you up to now, we did the calculations for strong acids or for strong acids or strong bases. What if we have vinegar? Acetic acid. About a weak acid. What's this percentage of dissociation? You're going to dissociate 100%? No. So can we just use the starting concentration to figure out what the pH is? You have to actually do an equilibrium calculation with the Rice table, figure out exactly how much hydronium we're going to get at equilibrium, convert that to the pH. Okay, so we have our Ka expression and we have our Ka value for acetic acid. And so if we start with 0.1 molar acetic acid, we just set up a Rice table. We assume that our hydronium concentration that we start with is about 0, because our starting concentration of acid is way higher than any hydronium that's present from water autoionization. For it, how do we solve for this? This a standard rice table calculation where we put in X and minus X for the changes, solve for X. We could just use a quadratic formula to solve for this, right? Most weak acids don't dissociate enough to make us have to do the quadratic formula. There are exceptions, but this one is small. So what we assume is that 0.1 minus X, when you subtract the X, is it going to make a big difference to 0.1? No. So we just do X squared over 0.1. That's easy calculation. Okay, solve for X. X is 1.3 times 10 to the minus 3 moles per liter. Moles per liter of what? What did we just solve for? We solved for the concentration of hydronium and the concentration of acetate ion, which is the conjugate base of acid. The question doesn't ask for that. The question asks for pH. How do we get it? Solve for the hydronium concentration, right? We just take minus log of our X value, minus log of hydronium, that gives us our pH. Okay. Is this essentially the same thing that we did in Unit 2? The only thing that's different is that first you have to decide whether the acid is a strong acid or a weak acid. If it's a strong acid, then the starting concentration is the final concentration of hydronium. Weak acid, and you do a rice table calculation. Solve for the hydronium calculation, solve for the hydronium concentration, and then you just convert that to pH. So really, once you know you have a weak acid, this is just Unit 2 all over again, except you convert to pH at the end. Okay, how about this one? Standard question. You make a 0.1 molar solution of an acid. You don't know what the acid is. They tell you that the pH of the solution is 3.4. And then they ask for what the Ka of the acid is. Did you find what the acid was just by figuring out what the Ka is and finding the acid that corresponds to that Ka? Possibly. Okay. Tell your neighbor how you would solve this. What does the pH tell you? What's it code for? It's code for the hydronium concentration at equilibrium for the acid-base reaction. So if I write my rice table, the pH can be used to tell me what X is. Okay? Because we know the pH, X is the hydronium concentration equilibrium. Get the hydronium concentration equilibrium by taking 10 to the minus pH, 10 to the minus 3.4, which tells us that our X value, which is our hydronium concentration, 3.9 times 10 to the minus 4. Okay, if we know X, how hard is it to figure out our Ka value? We just plug X into our original Ka expression, put that number in, we get Ka value. Is this exactly the same as Unit 2? The only difference is instead of them telling you in the problem what the equilibrium concentrations are, they give it to you in code in the form of pH. But it's an easy mathematical manipulation to convert it back to the concentrations that you need. Okay. What if you're mixing a weak base into water instead of a weak acid? What's going to happen? Put a base in water, it's going to react with water. What's going to form? The base is going to accept a proton from water to form the conjugate acid of the base plus hydroxide. Okay, so if we have acetate, acetate is the conjugate base of acetic acid. We can set up a rice table, right? Do we know the equilibrium constant for this? Could look up on a pKb table and find the pKb for acetic acid and convert that to a Kb value and use that Kb value for the rice table calculation. Or I already know the Ka value for acetic acid. We did it over here. It's 1.8 times 10 to the minus 5. Okay, if I know the Ka value for acetic acid, can I figure out the Kb for acetate? You take the pKa of an acid and multiply it by the pKb. Sorry, mixing things here. You take the Ka of an acid and multiply it by the Kb of the conjugate base of that acid. What do you get? You get 1 times 10 to the minus 14th. So if you know the Ka, you come up with the appropriate Kb. Okay, so we know the Ka value, 1.8 times 10 to the minus 5th. And the Kb times the Ka equals the Kw, so we can just solve for the Kb. Pretty easy. One extra layer, but you've been practicing rice tables all through unit 2, so this is just a little tweak one. Okay, once you know the Kb, how do you solve for this? Your rice table calculation. Rice table when you solve for X, what are you getting? Your hydroxide concentration. You can go from the hydroxide concentration to the POH, but the question asks for pH, so what would you do? You either take your hydroxide concentration, convert it to hydronium concentration, and then get your pH from that, or you take the hydroxide concentration, convert it to POH, and get your pH from that. Either one. Okay. How did we know acetate was a weak acid instead of a strong? Sorry. How do we know acetate was a weak base instead of a strong base? Where is it on the table? It's missing a negative sign right here. It's on the table. It is. Okay. This table ends at 1.8 times 10 to the minus 5th. Weak bases are the conjugate bases of acids with a Ka value above 10 to the minus 14. We'll talk more about that next. Okay, so it's a weak acid. Are you comfortable with those transformations, or do you want to see me do it? It's a mixed bag. Some of you want to see it. Some of you don't want to see me do anything more today. Your brain is full. Figure that out on your own. I have confidence that you can do it. Let me show you one more thing, and then you can stay and work recitation, or you can flee screaming because your brain and every other part of your body is now way full of acid base. Okay. One way to report how strong an acid is to give its Ka value or pKa value, right? The amount of that acid that actually reacts to form product is going to depend on how much acid we put in the solution, right? So we could just calculate the pH of the solution and use that as kind of a measure. There's another way that we talk about it, and we talk about the percent ionization. So we're just saying, of the starting material, how much reacts to form product? That's all we're saying for percent ionization. Okay, so percent ionization of a strong acid is 100%, right? Because all of it's going to react to form product. So typically we calculate percent ionization, not for strong acids, but for weak acids. How do we do that? We just calculate the hydronium concentration that we get at equilibrium. We divide it by our initial concentration of acid and multiply it by 100%. Okay, so what things give you a higher percent dissociation? If your weak acid is slightly stronger, what happens to the percent dissociation? It's going to go up, right? If your weak acid is weaker, less of it will react, so your percent dissociation goes down. According to Le Chatelier's principle, the concentration of the acid makes a difference. Interestingly, sometimes we have common ion things happening in acid-base reactions. And so if you already have some hydronium present in solution, what's going to happen to your percentage dissociation of an additional acid that you add? It'll actually go down. There's already product. We'll talk more about that next time. Okay, so we did this calculate 0.1 molar acetic acid. We had you calculate the pH, right? But we can do the same thing and have you calculate the percent ionization. Have you guys seen these arrows before? Show them to you. We're going to do them again in unit 3. So curved arrows are typically used by organic chemists to track the course of the reaction. And the curved arrow starts with the lone pair that's going to become a bond. Curved arrows say this lone pair forms a bond to a proton, which shows up in the product as this one of the lone pairs now has a bond to the proton. Okay, if you form a bond to hydrogen, how many bonds can hydrogen make? 1, right? So if one lone pair makes a bond to the hydrogen, what has to happen to this bond? Break. Electron in that bond travel to become on the oxygen. Okay. Know what the equilibrium expression is? Not in the right order. Okay, we set up our rice table. We can solve for x, right? That's just unit 2. When I solve for x, how do I use that in the percent ionization? Take the hydronium concentration, which is from the equilibrium line of our rice table, and that goes in the numerator of our formula. But then in our denominator, we use our starting concentration. A fraction, you multiply it by 100%, you call that the percent ionization. So it's not actually that complicated. Okay. So add the percent ionization. Want to hear the answers to the questions that students asked? You guys are like, oh, don't give me more. We'll do those in the next class. Work on recitation if you want. If you want, it is vitally important that you get this material sorted out in your head. It's part of your language and you don't have to think about it anymore. These skills, this is all the foundation of what we're going to do next. And it's a bolus of material. None of it is super tricky, but there's a lot of it.
My brain isn't.
Reacting with the water. Dealing with that.
Maybe you should say that.
We're only dealing with reactive pressures. Next time. We don't have to.
I think I might have
Using. A lot of this stuff you can sort through 4 or 5 layers. Oh. I'm making my way over. Who's? Strong acids, concentration to start with, can be completely converted to hydronium. So those are easy. Not easy if you only have the teeny bit. You have a little, have to count it. Then you have to include the auto ionization.
So.
Yeah.
Oh, we got the,
Value for that week.
for these questions, we're just gonna have to look at the K, like, we're gonna have the table, look at the K value, and then we
Look
can.
up the
plug
K
it in.
tape. value from the table and use that.
Okay, I see. It's not like. That's okay, great.
You might have a problem with it. Explain what the solution is
But then you
and
have to-
the concentration. And figure out what the data value is, but that's not how they
Sir.
We're being completely accurate. Concentration of hydronium to start with, we have some base level of hydronium because that's what water has, right? There. Not unless we have. That's it. Okay, yes, we have that. No, we don't care.
Process your emotions.
It's not your right to. I can't do that without.
Right.
Otherwise,
Right. Okay, that makes sense. This is great. I love that.
it's a lot to process right now. Start to do more. Terrible. Connect to what we did before. Okay.
Would you suggest, in order to get used to all of this, like just do a bunch of rice tables on different and just practice doing the.
I knew there was a chance. I almost missed it.
The chemistry tutor always has this problem, and you pause it and see if you could do it, and then he goes through it.
I'll definitely do that.
So if you just do the organic chemistry tutor, search on YouTube, a bunch of stuff will come up.
Okay.
So the, maybe that site before Kim. that teamed up.
So is the. Or
Actually, there are back of the book questions that you could do.
I think that some links on a certain website, I forgot what it was, but like every time I put it in, like it says like error. Like the website has like a problem. I don't know.
So the Chem Tours had all these. The real way to access those is you go in, sign on like you're gonna do smart work, and you get that page that says smart work, and then there's 5 different panels. There's one that says animations. On the animation, here's your chapter. Will have all of the tours for the base.
If you book Amazon, but you bought Smart Work,
It should still work.
it should still work.
Basically the same amount, but 6 weeks before Thanksgiving, I'm gonna literally, like, let me show you this. This isn't, I'm pretty sure I have mine done. It's over by then. How many? How many tests I have that week?
It comes up faster on my actual.
My anatomy lab. I'm just studying this weekend for them. Oh, yeah. You have to. Like, just hours of just like.
I just type in that, right? Sign in. See that? You see what's,
Yeah, but I just
Okay.
don't have access to the books. The
they're all in
animations.
the animation.
Okay.
Once you sign in. Click on the animation. Go to the chapter. Acid.
So these are explanations.
You're like smart work.
So sometimes those get included in the smart work.
Oh, yeah.
Felt good. Both of us had this whole time afterwards.
Yeah, so like every time it says like watch the.
Feels so good.
I can't watch.
Both of us afterwards.
Maybe if you do it this way.
Yeah, I know. I was like, I'm sorry.
No grades are out.
Okay, yeah, I thought just because
Yeah,
I got
try
the
those.
smart work instead of the book that I did.
I don't know.
Yeah, you should have access to it.
I don't know how many swells I did. And maybe it felt really
It's
good.
not, it's not.
I'm like, no, I don't think.
I paid my money, give me my.
I don't think.
Thank you. Yeah, I'll do that. See how that works out.
Still have any. So I'm like, I just, it's just. freaking weird. I don't like that.
Only 5 lectures left.
Oh, that's
That's
nice.
crazy.
I'm nervous or excited.
Well, if every lecture is like this one,
I know.
I think my brain's gonna explode.
Oh, baby.
This is a lot to process in lecture. And it doesn't help that prep before this lecture is gonna be less than.
Yeah. I hate to say it, but my prep was like this much of my day.
You only have so much emotional energy
Yeah.
and you just spend a lot of time creating emotion.
Yeah.
Put it all up. Yeah, so just go and process all of this. There's actually not as much there as you think.
I feel
As
like,
long as
yes,
you put it
that's
in
the way
your
my class
brain.
goes. It seems so bad. And then once you give it time, you
You're
look
like,
back and you're like, that's nothing. Like,
It's obvious.
yeah.
It's
There,
kind of
like,
like
it, like,
together.
memorized, and it's like,
So once you get what you
know,
hear, with
get
what
it.
you know from unit 2, you'll be like, oh,
We're cruising.
nothing. But it's in vocabulary.
Yeah. That's good. I'm like, wait.
Thanks, Dr. Ackroyd.
Thank you, Dr. Ackroyd.
It is kind of a demoralizing.
You said demoralizing?
For people that haven't seen acid-base reactions at all, it feels like
A lot.
a lot of material.
Then
It's not that many ideas.
so that was what I was thinking. I was thinking, actually, this is where a lot of concepts, I feel like I just took the test, I studied, I tried to study hard for it. I tried to master some skills, and now I'm looking at this and going,
Oh, yeah.
oh, pH, yeah, let's do that. Like,
Yeah.
but that, I think you're also right. I think for someone that hasn't seen acid bases, it's probably it's a lot. Which there is a lot of
Are
terminology.
the front of your mind right now. So some of the
It's
people in
true.
the class, it's been 2 years since they did Lewis structures and they didn't really understand them the first time,
Mhm.
because that happens.
And that is true as well. Hopefully. I'm the only one here.
Yeah. So you're not gonna offend
um,
anyone if you.
And it's not gonna offend anyone, I don't think, but I am looking at my exams now and I'm going, man, I feel like I understand concepts. At least when I'm studying them, I feel like I'm understanding them
Yeah.
more and more and more.
But that's just gonna increase, right?
Which then leads me to this train of thought where I'm going, I'm actually really excited for the final. Because I think the final is actually going to be a better representation of what I understand
Yes.
than me struggling and then seeing it at the end of a unit and then going, okay, I got to regurgitate this onto a test.
Yeah, but now you use it the whole time. And then when you go back to the final, you'll be like, oh, that's not so bad.
Exactly. And so I hate, it's a little, what is demoralizing is me going through these unit exams and being like, oh, I just feel like that's not a good, I feel like I could have a better
And you will.
reflection.
And you will,
And so, yes, but anyway, it's just sort of like a,
because when you take the exam, things are newer and you have to think harder. And you're using up your brain thinking harder.
Mhm.
And then that part of your brain that can catch mistakes is already somewhat
I've
engaged.
already caught it when I did like when I've gone through the test with you or looked over and been like, okay, I obviously need to iron that out and iron this out, but
You'll just get better at it.
yeah. So anyway, I say that, I look
Plus
around.
it's all
'cause-
multiple choice.
Plus it's multiple choice, but I look around just because I'm like, I have also been that student that took whatever it was, finance, I took finance.
Mhm.
And at the beginning of the year, he said, you know what? Or it was, I remember, but he's like, just, so you know, like, this is how the syllabus is laid out, this is how grades are, and at the very end, if you get an 85 on the exam or whatever, an A on the final, and it's lower, or it's more than what you've got in the class, I will give you the A. And I definitely abused that and took that for good advantage of that, and
But
it,
that's not really taking advantage of it. It doesn't help you.
in the moment, I thought it would, but it turned back around to bite me. But now I'm
In this
looking at it,
class, if you're working consistently the whole time,
Mhm.
it helps you.
it helps so much.
It
Yeah.
doesn't help as much in 105 because we're not using the same skills. the
Yes,
whole
it is
time.
about, which I do feel a little different about 105 because it is a little bit like, oh crap, I really need to make sure I understand.
Each unit could be its own class.
Yes,
That's not true for this
For
class.
this class, and especially this lecture, I was like, oh, I'm actually gonna understand this a lot more as it continues to go. Which is
So this class was just, here's all this vocabulary. Here's all these individual reactions. Connect to what you did before, make that part of your vocabulary. Then next time we can talk.
So I thought, I mean, I'll be honest, my wife is running in California this weekend, and so I drove her to the school because their flight was at like 6 in the morning, so I drove her to school at like 3. So.
I was awake at 3 too, if that
Oh, you're
comforts.
awake? Okay, you're doing much better. I'm struggling a lot more. But once we hit the race tables, I was like, oh, wow. The sleep is catching up to me.
It wasn't just you.
I'm
There were a couple
struggling.
other people that were like,
Okay, I was struggling hard.
well, look at math on this PowerPoint. It just is.
That also could be great. Yeah.
This is boring.
Feel like now that I have some sustenance, again,
Food is good.
it'll help.
Yeah, so I got up and did this and then
So yeah, why were you up at 3:30?
because I'm writing a grant proposal and teaching classes and planning a wedding and my brain wakes me up at 3. So
Are you usually a normal early riser?
I realize from tracking my sleep that I only get deep sleep before about midnight.
Mhm.
After 1, not, it's very rare for me to have deep sleep. So I go to bed early because that helps.
Yep.
So I did go to bed at 8 o'clock last night. So when I woke up at 3, it wasn't the end of the
It
world.
was awful.
I didn't actually get up till 4. Sort of could sleep.
How is, you're now less than a month away.
3 weeks from tomorrow.
Yeah. Is it coming together?
Food hasn't come together really.
Still trying to.
So we're trying to figure out something super easy, super inexpensive, and super good. And those things don't all go together. Yeah. And to make 5 flower crowns this weekend,
Is that for the bridesmaids or for?
the bride and the bridesmaids.
That's fun.
Actually, it depends. So my son wants my youngest daughter to be a groomsman. So there's a,
You want to be a groomsman?
she's fine to be a groomsman. Whether she wears a flower crown or not kind of depends on whether she finds a DI suit that will fit her in the right color. Because I told her I wasn't gonna buy her a suit because they cost too much.
So be only worn once, if
Yeah.
that's what you choose, yeah.
If I can buy a dress for $40 and it's not gonna be $40 to find a suit. And it was if everyone was wearing gray suits, that would be easy. There's gray suits everywhere.
I mean, does she fit yours? Like, yours too
But
right
it's not
now?
gray. It's supposed to be a beige,
Oh, okay.
which nobody wears beige suits right now. So I don't know what's gonna happen. She could probably wear my suit. She's taller than I am. She's about 2 inches taller than I am.
You're tall. She's
Yeah,
tall.
She's tall. And she's a swimmer, so she's big shoulders.
Yeah.
Like she's statuesque.
Yeah.
And I realized that we did something right. Lots of girls who are tall or broad-shouldered feel uncomfortable.
Yes, and they
It
all,
doesn't fit this.
their stigma of what a girl should be.
And that's worse than it used to be because of social media.
Oh, I imagine. Yeah.
And I borrowed a dress from her, and I'm still in my head thinking that this is my daughter, so I'm bigger than she is,
Mhm.
right? And I'm old, so I'm not the same size that I was when I was 20.
Mhm.
And so I just expect that I'm gonna be bigger than she is. And I
Yeah.
borrowed the dress and it was actually a little too big on me. And I was surprised and I said, oh, I thought that would be, I said something about the fact that I was surprised that she's bigger than I am.
Did you take that the wrong way?
Well, now, after I said it, I went.
Yeah.
Because there is that stigma potentially. And she just said, Mom, I'm a bigger human being than you are.
Oh, good for her.
I was like,
She's confident. Yes.
yeah, being a swimmer helps with that. Because swimmers feel differently about their bodies.
Yeah.
And runners feel differently about their bodies, but
They
there's,
also do.
but running is more linked to body shape and size, and swimming isn't. So swimmers can feel comfortable with lots of different. That was a bonus.
That's a good moment.
Exactly the thing I shouldn't have said. And she was like,
You took it.
kind of loves being tall.
I think it's funny because my Anna is the shortest now, or second shortest out of her sisters, 4 sisters. And the youngest ones are, they are so happy to be taller than Anna. That is a good thing.
Yeah, that's a good thing. The funny thing is, because I'm relatively tall, that tall, but
5'7", 5'8".
used to be 5'8", and now I'm 5'7.5", so I don't get to, I was 5'7 3/4", so I could claim 5'8".
That's higher than.
But that
the
puts me,
average.
93rd percentile. So my daughters, that seems normal because that's the height that I am. My oldest daughter is about 5 foot, average, and she's just always felt short. She isn't. All of the subsequent daughters that are taller than her, are like, I'm taller than you. So when my 5'9" daughter puts on her super tall Doc Martens, she wears those, she's really tall.
Did she not, did they not trip? Did Lily not trip with those on?
She doesn't.
Because every time I look at those, I'm like, those are like dense.
They're heavy.
Yeah, those are not like just a lightweight platform. They're dense.
It
Like,
took
if
her a
you roll
while
your
to break
ankle,
that in.
How do you not like walk and roll your ankle?
Well, they're stiff, so you don't roll your ankle.
But I guess you gotta be comfortable with them, but if, I can just imagine not being comfortable with them, making a turn.
You clearly haven't worn heels ever.
No, that's why it baffles me. I'm very impressed.
You learn how to walk in the shoes you're wearing, and Doc Martens are not bad compared to the range of women's shoes. How's that?
I believe
That
it.
is true.
I believe that.
So my daughter is an Anna as well. Yeah, and she was very excited. She said, I broke my Doc Martens in. She was all happy that she doesn't get blisters anymore. It's a big victory.
What are you writing your grant proposal for?
Let me show it to you.
Yeah.
I meant to do that in 106 just for fun. Maybe I'll do that next week. You guys don't get to see what scientists actually do, right?
It's true. It took me a while to figure out, wow, professors are not just educational teachers, they are scientists.
Okay, so which one's gonna come up?
Which I'll say, so I told you I TA for Physiology 305.
Uh-huh.
And our professor is leaving. This is his last semester because he is so frustrated with the design of just, he wants to do what he wants to do research wise. He has to adhere to the higher ups and the whatever. I don't understand it all, but he was ranting about it to me the other day. And it's actually, it could be very frustrating, I think, to be a professor, having to do research, but maybe not doing the research you want to do, and then having to find
There's a
funding for.
lot. The funding is a major issue.
He just, it makes him so mad. Yeah, so anyway, he's leaving to go work for a pharmaceutical company.
And then he doesn't have to write grants. Because the truth is you have to raise your own money to do the research. And if you don't have money to do the research you want to do, you have to do the research that you have money
And your
for.
job is then on the line as a, like,
So Matthew's brother, Josh, actually is involved in this work.
This with the diabetes and aren't you using like you're using the Cas9 protein, right? He was saying-
Yeah.
That's so cool. I think that's awesome.
The problem is that our work gets more and more complicated and gets harder and harder to explain. And then it's less successful in the funding process because it's no fun to read.
So what is it exactly that you're trying to do?
So there is a cell surface receptor that was first discovered in the context of anthrax toxin internalization. So you guys are too young to remember the whole anthrax toxin scare.
Worked on this.
My husband worked on this, and there's a protein called anthrax toxin receptor 2, which is one of the,
Right there.
yeah, that's one of the receptors that the anthrax toxin uses to get in the cell. Well, your body doesn't have it to let anthrax in, right? It has it because your body uses it somewhere. And when he was at Harvard, I wasn't involved in the research then. And we have good friends in Boston that were in our ward, and the husband was another postdoctoral fellow at Harvard, and they used to ride the train together. Well, this guy does angiogenesis, which is the process of growing new blood vessels, sprouting new blood vessels, which you need for wound healing and other things.
Uh-huh.
And, we used to have these conversations on the train station about their work. And one day Mike says to my husband, Ken, you know that CMG2 protein that you're working with, it's probably involved in angiogenesis. So they did these experiments that were secret experiments where my husband purified protein and delivered it to Mike, and Mike tested it in mice to see what it would do, kind of hush hush under the radar. And the proteins affect tumor growth and corneal neovascularization, and like it turns out to be really important. And so the three of us have spent the last 15 years, 16 years, just trying to figure out what the receptor is actually doing. There.
So what part does this fund,
Oh, I know what happened.
what will this part play into all of that then?
Okay, so it turns out we were able to use the Cas9 protein to actually remove that cell surface receptor from endothelial cells. And endothelial cells are the cells that end up forming vascular tissue. So that's what makes blood vessels and forms the vascular walls. Yeah, the vessel walls. And if you remove that, in order to form new blood vessels, there are growth factors that cause, like if you have a wound that's healing, for example, your body has to get the cues to know where to build the new blood vessels. So they have to grow in a certain direction, right?
These are VFGF, VGF.
Yes, those are the growth factors. And what happens is in response to those growth factors, individual endothelial cells actually travel over your extracellular matrix in the direction of the growth factors.
This is your chemotaxis.
Chemotaxis. So there's these cues that tell the endothelial cells what direction to move in order to appropriately form the vascular tissue that you need. And when we take out this receptor, CMG2, they still move, but they move in random directions. So they totally lose the ability to respond to the growth factor when this receptor is missing.
And it acts as this intermediary in that pathway then? That's what you're saying?
Yes.
That CMG2 is a key intermediary in the pathway.
So there's
required.
another important, super important pathway, like people won the Nobel Prize for discovering it, that involves signaling, intracellular signaling through what's called the Rho pathway. And that's involved in how cells travel. And it's already known that that pathway is involved in directional travel. So if we have this receptor and it's responsible for responding to growth factors in a certain direction, and you take it out and they stop being able to do that. And there's evidence that suggests that the receptor is involved with this other pathway. Then what we're trying to do is track how this receptor manipulates the other pathway to tell the cells how to respond to growth factor or not. In terms of drug discovery, that matters because there's a whole bunch of pathogenesis, like inappropriate things where you have blood vessel growth that's not supposed to be there. We typically apply for grants through the NIH, branch of the National Institutes of Health, Eye Institute. And one of the things, there's a lot of eye diseases that come from inappropriate blood vessel growth in the eye.
Or drug. Or just
It happens in response to diabetes, for example. It happens in response to
communication.
eye injury. Like if you have if you wound your eye, your body responds by growing new blood vessels, but that's a bad idea when it's your cornea. We do a lot of corneal transplants, which are great, but your body thinks it's a wound. And so, yeah, a fairly high percentage of corneal transplants fail because of corneal neovascularization. Well, if we can say this is a protein that we can target with the drug
Yeah.
to turn that off. And cancer has to recruit new blood vessels and grow them. In fact, there's a common anti-cancer drug that targets new blood vessel growth, but it targets VEGF, which is a growth factor that's responsible for a whole bunch of things. So there's huge side effects. And the body is fairly good at workarounds for that. So drug resistance develops fairly quickly for that drug. But this system, actually, it looks like it's targeting multiple growth factors at once, at least 3 that we know about, or in response to multiple growth factors, which means it's harder for the body to come up with a workaround. Yeah. So we're looking at something that potentially is low side effects, low development of drug resistance, high effectiveness, but we have to track the whole signaling pathway first. And that's what we're applying for money to do. Over and over, we're applying for money to do. And they say things like, whatever.
So this is a dumb question, but I've listened to a couple of proposals just here and there when I have the chance. How do people say no to you? Like, this sounds fascinating and sounds like super,
They don't say no, they say,
they limit you then on like, we're only gonna
Give you a
do this
score.
much?
give you a score.
Okay,
So they score you on significance and innovation and how good your approach is, and they give you a score for how good that, like, you're qualified to do this particular.
Yeah.
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 And based on the score, they rank you. And there's a cutoff. So you get a percentile rank to everybody else who
that
applied.
might be doing something similar.
Everybody else who applied it. So what happens is we're typically just below the cutoff. 3 different reviewers and 2 of them love it and the third one's like, nah, I don't think so. Even if their criticisms are actually false, it still doesn't get credit. You have 12 pages to outline all the background.
Which is not enough.
It's not enough. Plus all of the experimental data you've already collected to show that you do it.
Yeah.
And it is going to work. And justify any potential concern that any possible plus put figures in there so they can see the data. So it's this constant game of what do you put in and what don't you? So this is a resubmission of a previous grant. So we're supposed to respond to the reviewer criticisms. Take space. And then one of the reviewer criticisms, this is really dense. Well, what do? So every sentence, you're like, can this be compressed? If you compress, does that make it harder to read? Can I make this a little bit harder to read because I really need it somewhere else? Start even worrying about, you put 2-point spacing between subheadings or only 1-point spacing. So like it's.
And are these grants, are these like from universities, are they federal grants or?
We're submitting it to the National Institutes of Health. So it's a collaboration between my husband and I and Boston.
Now, you enjoy, I say enjoy because you know that you're good at this,
I am
at writing.
grateful the opportunity to do it.
But as far as writing, like that's something that
I'm
you
happy to be
feel-
still part of the science.
Mhm.
Like I'm really grateful that I get to be a part of it, but it's painful. Like it's probably the hardest kind of technical writing that you can do.
You told me though that you would like, you feel. that you
It
do
turns
very
out that
good.
I'm good at it.
Yeah, okay, there we go. That's what I'm trying to.
It turns out that I'm good at it.
You're very good at this.
And I'm not someone that assumes that I'm just good at things.
I'm
Actually, I'm
doing it for you.
reasonably good at this. And I don't like. That's what I always right? I'm trained as a organic chemist,
Yeah.
so I think this is I don't go along. But, you know. Probably start the.
When do you hear back from them? You just recently submitted, or,
It's not actually supposed to, it's due November 5th.
oh,
So we're in the
refining stage.
refining and we possibly spectacular new data can come up with between now and November. Ups our chances. Actually, Matthew's brother is doing work associated. It would help if I'm in the right class.
Chemistry.
Online.
It's not a science eating class. He's just like, some guy. It's a speeding ticket. Pretty good.
You go on to Learning Suite and see if the online tab has just disappeared and it won't be seen. I set up a meeting this morning.
Still there.
Yeah, no.
Still there. Around my hand. That is. That was. That's great.
Oh my gosh.